Welcome back to the Neural Intel Pod. Today, we're diving deep into quantum computing, specifically how researchers are using a surprising technique, SAT solving, to make quantum computers, well, more efficient.
It is pretty fascinating, like how a classic logic problem is now being applied to this cutting-edge technology.
Right, and we're going to be unpacking an article from Amazon Science. It's called Using SAT Solving to Optimize Quantum Circuit Mapping. It details a new method that could significantly speed up the process of running complex quantum algorithms, on the limited hardware we have available today.
Yeah, it's all about bridging that gap between the complex algorithms that we want to run and the physical reality of the quantum computers that we have.
Okay, so before we get into the nitty-gritty, can you give us like a quick quantum computing 101?
That's it is.
Some of our listeners, might be wondering, what is a quantum circuit?
Of course. So imagine a classical computer circuit, with its logic gates, the A and D, the OR, the not T gates, and so on. A quantum circuit, it's similar, but instead of bits, it uses qubits, which can be in a superposition of states. And these qubits are manipulated by quantum gates, analogous to those logic gates, to perform computations.
Okay, so it's kind of like a quantum version of a classical circuit, but with that added twist of superposition. What makes these quantum circuits so tricky to actually work with?
Well, the algorithms that we want to run are often very, very complex, but the physical layout of these qubits on a quantum chip is much simpler. It's almost like trying to fit a giant jigsaw puzzle onto a tiny board.
So how do we get these complex circuits to actually run on the hardware?
That is where the quantum compilers come in. Their job is to essentially translate those complex algorithms into a sequence of operations that the physical qubits can actually perform.
It sounds like a really, really tough translation job.
It is. And one of the biggest challenges is qubit routing. Qubits need to interact with each other to perform those calculations, but they might not be physically connected on the actual chip.
So how do we get around that?
That's where the swap gate comes in. It allows us to move qubits around, essentially swapping their positions so that they can interact.
So it's like rearranging furniture to make space for a conversation.
Exactly. But here's the catch. Swap gates are costly. They add extra steps to the computation, which increases the chance of errors. So the fewer swap gates we use, the better.
That makes sense. So minimizing swap gates is key to making quantum computing more efficient.
Precisely.
Yeah.
And that's where this research comes in.
The article dives into a really cool example to illustrate this problem. Implementing the quantum Fourier transform on the Rigetti Aspen M3 quantum computer. Can you walk us through that?
Sure. The Rigetti Aspen M3 has a specific layout of qubits, like a grid with certain connections between them. Now, the quantum Fourier transform, or QFT, it's a famous quantum algorithm, and it requires a specific arrangement of these qubits, a 3-qubit ring structure.
And the Aspen M3 doesn't have that structure.
Not directly, no. So the first step in circuit mapping, which is figuring out how to run the algorithm on the hardware, is to try to place the qubits in a way that matches the QFT's requirements. But in this case, because of the Aspen M3's layout, it just doesn't work.
So then what happens?
That's where that qubit routing using the swap gates comes in. By strategically inserting these swap gates into the circuit, we can essentially shuffle the qubits around and create those necessary connections for the QFT to run.
Oh, so it's like solving a puzzle, moving those pieces around until they fit.
Exactly. But remember, we want to use as few swap gates as possible to keep things efficient.
Right, right. So what were the existing approaches to circuit mapping and why weren't they ideal?
Well, there were two main methods. Solver-based algorithms and heuristic algorithms. Solver-based algorithms, they were great at finding the absolute minimum number of swap gates, but they were really slow. Heuristic algorithms, they were much faster, but often ended up using more swap gates than necessary.
So it was a trade-off between speed and optimality.
Exactly, and that's what makes this new SAT-based approach so exciting.
Let's get into that. So we're going to get into this new SAT-based approach to quantum circuit mapping. Can you unpack that for us? What is SAT and how does it apply to quantum computing?
SAT stands for Boolean satisfiability. It's essentially a logic problem where you have a set of variables that can be either true or false and a set of logical statements that connect those variables. And the goal is to find an assignment of truth values to those variables that makes all the statements true.
So it's like a really, really complex logic puzzle.
Exactly. And so what the researchers did was they cleverly encoded this problem of finding an efficient circuit mapping as a SAT problem.
Hold on. How do you turn circuit mapping into a logic puzzle?
Well, you can think of each possible swap gate as a variable. And
Eh,
the logical statements, they represent the constraints of the problem. So the specific qubit connections that are required by the algorithm and the layout of the chip.
Oh, so it's like saying, can I fit these pieces together in this way using only this many moves?
Precisely. And they used a SAT solver, which is a program that's designed to solve these kinds of logic problems to find the solution.
So they basically asked the SAT solver to find the most efficient way to map this circuit onto this hardware.
Exactly. And what's really clever is that they used an incremental approach. They started by setting a limit on the number of swap gates that are allowed, and then they gradually reduced that limit, checking with the SAT solver at each step to see if a solution still existed.
Oh, so it's like they were saying, can we do this with 10 swaps? How about 9, 8, and so on, until they found that absolute minimum.
You got it. And this incremental approach, combined with some parallel processing techniques, made the whole process much, much faster.
And how much faster are we talking about?
Well, they achieved a remarkable 26 times speed improvement compared to the previous solver-based methods.
Wow, that's huge. So they basically found a way to get the accuracy of the solver-based methods, but with the speed of those less accurate heuristic algorithms.
Exactly. And they managed to reduce the compilation times from hours to minutes, which is a game changer for researchers working with these complex quantum algorithms.
And they didn't just improve the speed, they actually achieved better results too, right?
Right. On average, they achieved a 26% reduction in swap counts compared to those heuristic methods.
So they found a way to run these algorithms more efficiently and more accurately.
Precisely. And it's important to remember why this efficiency is so crucial. We're still in the early days of quantum computing, and quantum hardware is limited and it's expensive. Every qubit is precious, and every operation carries a risk of error. By minimizing the number of swap gates, we're minimizing those risks and making the most of these valuable quantum resources.
It's like optimizing every single move in a delicate dance.
Exactly. And this efficiency is critical as we develop more complex quantum algorithms to tackle those real-world problems. It's all about making those algorithms practical and scalable.
So this SAT-based approach, it's not just a theoretical improvement, it has real-world implications for the future of quantum computing.
Absolutely. This research is paving the way for quantum computers to tackle problems that are currently intractable for classical computers. We're talking about potential breakthroughs in medicine, in material science, in finance, in artificial intelligence. The possibilities are truly mind-boggling.
It is inspiring to see how researchers are combining seemingly disparate fields like logic problem solving and quantum mechanics to push the boundaries of what's possible.
It is quite remarkable.
We're back and ready to wrap up our deep dive looking at SAT solving and its impact on quantum circuit mapping.
Yeah, it's been pretty interesting exploring this research.
It has. We've seen how researchers are combining this like classical logic with quantum technology, to make quantum computing more efficient and powerful. But what I find most exciting is what this research tells us about the bigger picture, the future of quantum computing.
I think what's fascinating is that we're not just replacing these classical computers, right, with quantum ones. We're actually finding ways to leverage the strengths of both.
Yeah, it's like they're working together, each one kind of playing a crucial role.
Exactly. And this research really highlights that beautifully. We're using these classical SAT solvers to tackle this like core challenge in quantum computing. It's a testament to the power of cross-disciplinary thinking.
And this trend of combining classical and quantum computing, I mean, it's likely to continue, right?
Absolutely. As quantum computers become more and more sophisticated, we can expect to see even more creative applications of these classical computing techniques to optimize their performance.
It's like building a bridge between the computing power we have today and the potential of quantum computing in the future.
And that bridge is essential for navigating, the challenges that lie ahead. We're still in those early stages of quantum computing, and there's so much that we don't know. But this research shows that we can make significant progress by leveraging the tools and the knowledge that we already have.
It's like using a familiar map to guide us through like uncharted territory.
Precisely. And the potential rewards are just enormous.
Mhm.
We're talking about potential breakthroughs in fields like medicine, material science, finance, artificial intelligence. The list just goes on.
It's mind-blowing to even think about all the possibilities, from designing life-saving drugs to developing these new materials with incredible properties. quantum computing could, like, revolutionize so many aspects of our world.
And this research is a significant step toward making those possibilities a reality. It's not just this theoretical advancement, it's laying the groundwork for practical applications of quantum computing.
It's inspiring to see the creativity and the ingenuity driving this field forward. Researchers are constantly pushing the boundaries of what's possible. It's an exciting time to be following all these developments.
Indeed. And for anyone who wants to delve a little deeper into the technical details of this research, the full article is available on Amazon Science, and we've included the link in our bio.
It's a must-read for anyone who's interested in the future of computing and the incredible potential of quantum technology.
And as we conclude this deep dive, we want to leave you with a question to ponder. If we can already achieve such remarkable results by bridging classical and quantum computing, what other groundbreaking innovations might emerge from this synergy in the years to come?
It's a fascinating question. We're standing at the dawn of a new era of computing, and the journey ahead is full of potential and wonder.
Thank you for joining us on this exploration of SAT solving and its impact on quantum circuit mapping.
We hope this deep dive has sparked your curiosity about the world of quantum computing and all the incredible possibilities it holds. Until next time, keep exploring those frontiers of knowledge.